Hello everybody and welcome to this first episode of our Back to Basics series. My name is Xavier Rodriguez and I'm an application specialist here at Waters. For many years my focus has been sample prep, and this is precisely the topic of today's session. Hope you like it. We'll go through a first introduction on sample preparation to quickly dive into the basics of solid phase extraction, the key parameters, the different chromatographic modes that we can work with, the typical protocols, and we will try to show how to work practically with solid phase extraction through a video. Finally, we will end up with some practical considerations regarding formats, processing, and strategies to work with SPE. So, without further ado, let's start. Probably, sample preparation is the most tedious thing that you have to do in your lab. It is a manual process. It is time-consuming, it is often an expensive step of your protocol. So who wants to do sample prep? Or, in other words, why do we have to do sample prep? Because probably nobody in an ideal world would like to do sample prep. Speaking with scientists like you tell us that you would like to keep sample preparation as simple as possible. You would like to avoid the use of expensive techniques. You would like to be able to develop quickly robust methods. But also, you have to ensure that you get the desired detection limits, that you avoid as much as possible matrix effect. You want to obtain the maximum specificity out of your sample preparation methods. You want, of course, to enlarge the column lifetime and minimize the downtime of your instruments. So, of course, we have to find a compromise between a minimal sample prep and a sample prep that allows you to get the desired results. This is what we often call as good enough sample preparation. What are the goals that we are trying to achieve when we work with sample preparation? Well, we want to remove interferences that will enable us to have a better chromatography or a better detection. We want to be able to get to more confident analytical results and to have less instrument downtime. We also want to enrich our samples to get to this very high detection sensitivity. And we also want, through sample preparation, to make sample more compatible with the analytical technique that is following. For instance, to match the solving strengths, eliminate ion suppression, etc. In fact, the ultimate goal is to make your lab more productive, with lower limits of detection, with the systems running more for longer periods, to be able to analyze more samples with less time, to minimize the costs in manpower and in equipment maintenance, etc. So, how much cleanup is actually needed? How much do I have to work my sample prep? Well, that will depend mainly on three factors. The sensitivity that you want to achieve, the analytical technique that you're using. It's not going to be the same to work with a UV or to work with a high-end tandem quad. The specificity, the sensitivity of the analytical technique will greatly define the extent of sample prep required. And of course, the complexity of your matrix. It's not going to be the same to work with a fairly easy matrix such as drinking water, or to work with oil, or to work with whole blood, or to work with tissue. So you have to think about these three parameters, these three variables, when starting to develop a sample prep method. Because of course, there's not going to be one solution for every single scenario. Depending on the scenario, you will have to work more or less your sample preparation methods. That's why, in fact, there are different and many possibilities regarding the sample prep techniques of choice. You can work, or you can decide to work with a very simple option like solution, or even a filtration or centrifugation, or you may want to try to clean more your sample, maybe using a more complex technique like liquid-liquid extraction. In fact, liquid-liquid extraction is a good technique. You can get a good cleanup using liquid-liquid extraction, and you can also enrich your analytes. But it is clear that it is a cumbersome technique. It is relatively expensive. You use a relatively high amount of organic solvents, and it's probably not the greenest option in the world. On the other hand, we have solid phase extraction. In fact, solid phase extraction is just a chromatographic technique applied to sample preparation. So everything that you need and that you use probably every day when developing LC methods, you can also apply to SPE, to solid phase extraction. With solid phase extraction, you can relatively easily clean up your samples to concentrate your analytes. It is a technique which is relatively easy to automate, and the fact or the availability of different solvents, different formats, and different solvents that you can play with make this technique a very good choice for your sample preparation. Of course, it has some drawbacks. For instance, you may need to perform multiple steps in your process, and it is often a technique which is not fully understood. But we will show you during today's session and the second episode of this series how to overcome or how to make this sample preparation easier using solid phase extraction. Let's think now of the different factors that influence the SPE performance, the different parameters that you have to take into account when developing a SPE method. And we can speak about 4 parameters. 2 of them which are fixed, which is the matrix that you have to work with and the analytes that you have to analyze, and 2 of them that you can choose, that you can play with. The solvent that you're going to be using and the solvent that you may use. And it is going to be the interactions between these 4 actors that will determine the success of your sample prep method. Let's start by speaking about the analyte and the matrix. Before starting any work in the lab, you need to define a protocol to follow based mainly on the characteristics of the analyte and the matrix. What are those characteristics? For instance, we will be focusing on the polarity, or we have to take care about the polarity of the analytes. What are the functional groups that this analyte has? We will be focusing also on the potential presence of ionizable groups. We'll have to think also of the solubility of this analyte in different solvents. Is it soluble in water? Is it soluble in different organic solvents? So we have to think about all of this when defining or sample prep approach. The same holds true for the matrix. We have to know what are the properties of the matrix and how do they relate to the analytes. For instance, if we are dealing with relatively polar analytes present in an hydrophobic matrix, well, probably it's going to be a relatively easy scenario. While if we want to analyze very hydrophobic analytes into a very hydrophobic matrix, then we may have a problem, because it's going to be very easy to get rid of most of the matrix without losing our analytes. The other two parameters are the solvent and the sorbent. Let's start by this later one, the sorbent. There's many different sorbents available in the market, but generally we can be speaking out 4 classes. We can be speaking out reverse phase sorbents, normal phase sorbents, and then ion exchange or mixed mode sorbents. Depending again on the nature of your analytes, on the nature of the matrix, we will be choosing one or the other. We will see how to choose the different sorbents in a while. And then we have to, or we can also choose the solvents that we're going to be using throughout all the process. What's going to be the solvent that we're going to be loading or sample into the SPE with? What's going to be the washing solvent that we're going to use? What's going to be the elution solvent? Well, again, that will be defined, or that will depend a lot on the characteristics of the sorbent, the analyte, and the matrix. These are, or in this table you can see commonly used SPE solvent and some of their properties in terms of polarity and in terms of water miscibility. You can see, for instance, that on top of this table you have hexane, isooctane, chloroform. These are non-polar solvents. These are weak solvents for normal phase, but strong solvents for reverse phase. If we move down on this table, we'll find the more polar solvents like water. These solvents are going to be strong solvents for normal phase, but weak solvents for reverse phase SPE protocols. We have spoken out sorbents, out the different sorbents available. How are we going to choose between all these sorbents? Well, we can choose them based on different parameters, but mainly we can distinguish 3. The first one being the sample solvent. Is the sample that we have to work with dissolved in an organic solvent? If yes, then probably the easiest or the more logical path would be to work with a normal phase SPE solvent. We could also work in reverse phase mode, but using the pass-through strategy or the dispersive SPE strategy. We'll cover the different strategies later on during this presentation. On the other hand, if we have our sample in an aqueous solvent and maybe buffers, then the most logical approach would be to work with reverse phase SPE. We also choose our sorbent based on the strategy of the SPE method. Again, we'll cover that later on. And finally, we can choose the sorbent to use depending on the properties of the analytes. Is it polar analyte? Is it ionizable? For instance, if it is ionizable, we may think about using the ion exchange modes. So, the typical sorbents can be classified depending on the chromatographic modes that we're going to be working with. So we can speak about normal phase sorbents, revert phase sorbents, and ion exchange and mixed mode sorbents. Let's speak first about the normal phase sorbents, or about normal phase SPE. How does it work? Well, normal phase SPE is usually used to retain moderately polar to polar compounds from a non-polar matrix. That would be the ideal scenario. So these sorbents, these normal phase sorbents, are typically either polar functionalized bonded silicas, so we are bonding a polar group into a silica base. Examples of that are the cyano, the aminopropyl, or the diol sorbents, or polar adsorption media, which is not functionalized, and this can be silica, fluorosil, and alumina. What are the retention mechanisms? Well, retention under normal phase SPE is predominantly due to polar groups on the sorbent interacting or retaining polar functional groups of the analyte. These interactions are all polar interactions, but they can be of different origin. Normal phase can retain by hydrogen bonding interactions, by dipole-dipole interactions, or by dispersion interactions. And once a compound is retained by one of these mechanisms, then we need to use a strong enough solvent to disrupt this binding mechanism. And this is typically a solvent which is more polar than the original sample matrix or extraction solvent. So let's see in a little bit more detail how this normal phase retention mechanism works. Usually, the typical analytes to work with normal phase are small analytes with a high number of polar functional groups. These are the compounds that will have a greater retention in normal phase. One example would be salicylic acid, a small structure with relatively high number of polar groups. Generally speaking, the analytes which interact with the stationary phase by hydrogen bonding have the strongest retention, followed by the dipole-dipole interactions, and finally the dispersion interactions. For instance, primary amines and carboxylic acids provide strong hydrogen bonding interactions with silica and are therefore well retained by normal phase. Retention also increases, of course, with increased number of functional groups. For instance, an analyte with 2 hydroxyl groups would be better retained than one analyte containing just 1 hydroxyl group. Once retained, we have to elute our analytes from the sorbent. In this design here of the cartridge, you can see 3 different analytes: the blue, the red, and the yellow, which will flow through the cartridge at different speeds. For instance, the blue analyte is the most non-polar one. It is the one that likes the non-polar solvent the best. It is not well retained with a normal phase sorbent, so it will be the first one eluting. The red one is moderately polar, so it likes a little bit the stationary phase and slows down so it doesn't flow as quickly as the blue one. And finally, the yellow one is a very polar one, so it is very much retained by the polar sorbent in normal phase SPE. So it will be retained a lot and will need a very strong solvent to elute it from the cartridge. And this is the typical protocol, the typical method that we will be following when working with normal phase SPE. First, we will condition our cartridge with a strong solvent. Then we will equilibrate our cartridge with a weak solvent, and only then we will be loading our sample into the cartridge. Then we can wash the cartridge, try to use the strongest possible solvent without diluting your analyte, because that will enable you to clean as much as possible your sample. And finally, we will be eluting our analytes from the cartridge with a strong solvent. Whenever possible, you will be able to maximize the cleanup by using the weakest possible strong solvent that will be able to elute your analyte. On the right hand side of the slide, you have typical solvents used in normal phase SPE, with the hexane being the weakest solvent and water being the strongest solvent. Let's speak now about reverse phase solvents. How does it work? How does reverse phase SPE work? Well, reverse phase SPE is usually used to retain mid to non-polar compounds from polar and moderately polar matrices, typically aqueous matrices. Polar interactions occur between an analyte introduced to a reverse phase solvent in either a polar sample or solvent, which can include a diluted organic extract, or an aqueous sample such as water, plasma, or milk. Examples of reverse phase solvents are alkyl bonded silica like C18, C8, or C2, copolymer based solvents such as Oasis HLB, or even carbon based absorption media. How does the retention work? Well, retention of the analytes under reverse phase SPE conditions is predominantly due to the attractive forces between the functional groups of the silica surface and the carbon-hydrogen bonds in the analyte. These interactions can be van der Waals forces or dispersion interaction. And once a compound is retained by one of these mechanisms, elution is induced by using a solvent which disrupts this binding mechanism. This solvent is typically non-polar, such as methanol or acetonitrile. So in reverse phase, we are typically loading our sample in aqueous, and then we are eluting in high organic, usually methanol or acetonitrile. Again, once retained, we have to elute those analytes from the cartridge. Again, the three examples of three analytes with three different colors. The blue one being the more hydrophobic analyte, so it is the one being more retained. Then the red one is a moderately polar compound which flows a little bit faster through the solvent. And then the yellow is the more polar analyte, the one that will be less retained. Again, the typical structure of a method when working with reverse phase SPE. Again, the 5 steps in the process: the conditioning, the equilibration, the loading, the wash, and the elution. And at the right, the typical solvents that we're going to be using. Again, we will be loading the weakest solvent possible, so water. We will be using organic solvents such as acetonitrile or methanol to elute our analytes from the solvent. And now it's time for the video. In this video, we're going to be demonstrating the work with reverse phase SPE. We're going to be working with setback C18 reverse phase silica-based solvents or cartridges, and we're also going to be using the Oasis reverse phase polymeric cartridges. we're going to be working with grape juice as a matrix. We have here the powder, and this grape juice powder contains components of different polarities such as sugars, organic acid, dyes, and flavors. And this is just a powder dissolved in water. Regarding the solvents to use, we're going to be using solvents of different strengths. For instance, for elution, we're going to be using vodka, which contains 40% ethanol, and we're going to be dilute this vodka 1:1 with water for the wash step. Then we're going to be using isopropanol for the conditioning step, and we're going to be using water for the equilibration. So let's start with the experiment. The first step, the standard protocol, is to condition. And in reverse phase, we're going to be conditioning with a strong solvent. And in this case, we're going to be using isopropanol. Both in the conditioning and the equilibration steps, we don't have to take care of going very slowly. We can go relatively fast. So the second step, as I said before, is the equilibration, and we do that with water. We just pass some water through the cartridge. Once equilibration is finished, we load or sample. And at this point, it is critical to load or sample slowly. We typically say that we need to allow some time for the analytes to interact with the sorbent, and for that we have to load slowly. We say that approximately we're going to be loading at a speed of 1 drop per second. Please note that the dyes, which are relatively hydrophobic, are being retained on the top of the cartridge, while what it is eluting from the cartridge has no color. It is perfectly clear, and this is containing the more polar components such as sugars or some organic acids. You can see clearly the color of the dyes on the top of the cartridge and the liquid with no color that we have collected. The next step is the washing step, and we're going to be using a 20% ethanol in water solvent. And here we're going to see how we can get rid of some interferences. In this case, let's imagine that the interferences are the red dye, and we see that with this 20% organic solution, the red begins to flow through the cartridge, while the blue dye still stays on top of the cartridge. So we can selectively elute the interferences, in this case the red dye, from the cartridge without eluting the analyte, which is in fact in this particular example the blue dye. And finally we are going to elute, and for that we use the vodka, so 40% ethanol in water, a strong solvent for reverse phase SPE. And again we have to perform the elution slowly, around 1 drop per second. And here again we see, and now we see clearly how the blue begins to quickly flow through the cartridge, through the sorbent, and we can finally elute or elute our blue dye without any hint of the red dye, which are the interferences. So you see that there's no blue left in the cartridge, while we have collected all the blue in the vial. I hope you have enjoyed the video. Now let's talk about other parameters that we have to take into account when working with SPE. and the first one being the configuration or the format to use. There are different formats to work with SPE. The most commonly one used is clearly the cartridges. You can see some examples of cartridges at the back of the image, and depending on the amount of sample that we want to work with, we'll choose a smaller cartridge, a cartridge with less sorbent, or a cartridge with a higher amount of sorbent. In the middle of the image you have the two 96 well plate formats. On the left the standard one, on the right the microelution one, that will allow you to work with extremely low volumes of sample. And in the front part of the picture you have the so-called online SPE devices. Another choice that we have to make is how are we going to be processing our samples. First option, the easiest option, is to process by gravity. The gravity force will make the sample and the different solvents flow through the cartridge. The second option to process samples by SPE is vacuum. And in the image you have a typical vacuum manifold for cartridges. It consists on a glass chamber with a plastic cover which has holes on it, and there you can adapt, you can insert, you can connect your cartridges, your SPE cartridges. By connecting this chamber to a vacuum pump, you will create a depression inside the chamber, and this will suck the samples and the different solvents through the sorbent and into the waste tubes which are inside the chamber. We have also the same or very similar vacuum manifolds for 96 well plates. But just as you have seen in the video, we can also use the positive pressure to process our samples through SPE. In this case, and as you have seen in the video, we can use a syringe with a plunger to make the sample pass through the SPE cartridge. Another option, speaking about positive pressure, is to use what we call a positive pressure manifold or positive pressure processor, in which the force is applied by a positive flow of nitrogen that is going to go through the cartridges or the wells of a 96 well plate and force the sample and the different solvents through the sorbent. Another option to work with positive pressure is to use the Auto Specialist Positive Pressure Manifold. This is a semi-automated SPE manifold which works with programmed methods. These methods reduce user variability and allow the auto to improve method robustness and sample reproducibility. The system is compatible with standard and microelution 96 well plates, as well as with 1cc, 3cc and 6cc cartridges. And finally, there are also different options to fully automate the SPE process. And here, as an example, you have the extraction plus module, which combined with the Andrew Plus pipetting robot enables a fully automated SPE, and it is compatible both with plates and with cartridges. And to end up, I would like to speak about the different strategies that we can work with when speaking or when working on SPE. We'll be speaking about dispersive SPE, pass-through SPE, or retention, cleanup, and elution SPE. Let's start by the latter, the retention, cleanup, and elution strategy. This is the strategy that you have seen in the video. In this strategy, we load our sample trying to retain our analyte, so we're loading using a weak solvent. Then we wash our samples trying to eliminate interferences but not losing our analytes. And finally, we use a stronger solvent to elute our analytes from the cartridge. Another strategy is what we call the dispersive SPE. In this case, the solvent is not packed into a cartridge, but we're using a bulk solvent that we introduce into a tube, and then we pipe it or sample or liquid sample into this tube, and by shaking we try to force the interaction between the interferences coming from the matrix and the solvent. Like that, then we will centrifuge and take the supernatant, which will contain all analytes, but will contain less interferences than the original sample. And the third option is what we call the pass-through mode, or if you want another way to call it, is the chemical filtration SPE. In this case, we are also using SPE cartridges, but we are loading the sample in such conditions that the analytes will not be retained on the sorbent. We're only aiming at the retention of the interferences. Okay, so for instance, let's say that in our sample we have very hydrophobic interferences, such as fatty compounds, that we want to get rid of, and we have our sample in organic. By passing this sample through a reverse phase SPE sorbent, the very hydrophobic fatty content of our sample will get retained by thanks to the high strength of the solvent. We're using an organic solvent. The analytes will not be retained. Of course, this is a very quick process. It's a very quick process. We just have to use the SPE cartridge as if it was a filter. This table compares the three strategies. The key takeaways here are that from one side, both the dispersive SPE and the pass-through SPE try to maximize the retention of the matrix, while the retention cleanup and elution strategy tries to maximize the retention of the analytes, and that it is with the retention, cleanup and elution strategy that we can obtain the most effective and selective cleanup. Also, typically we will be using the dispersive SPE and the pass-through SPE for multi-residue methods, while we tend to use the retention, cleanup and elution when the number of analytes is reduced, or when we are analyzing analytes that belong to the same family with relatively homogeneous properties.